So from Calc 1, there's this problem. Well, there's a lot of problems. Where you have a sheet of paper or a sheet of something, and then you cut out a value of x from the box, from the rectangle, and then you fold it. So if we want to look at this like as a sheet of paper or just a different set of dimensions, let's say this is, let's not make it a sheet, let's make it nicer numbers. Let's say this is 12 and this is 8 inches, meters, centimeters, whatever. So after we make that cut, then this long side is 12, but then we cut out a measure of x on the left and on the right. So there's two x's that we cut out. And then this is 8, where we cut out another couple of x's on the left and the right. And so we're trying to maximize the volume. And the height is x. Oh, this isn't the example I wanted.
Oh, just rewrite this down?
No.
Okay.
Sorry. Well, in calculus, you would just, this is what you're trying to maximize. You would take the derivative of it and set it equal to 0 and all that stuff. So this isn't what I wanted. Let me try something else. Let's say you're trying to maximize area. Area from a fixed perimeter. Fence. So let's say your fixed perimeter is 48. So you want to make a fence with a 48 feet of fencing, and you want to try to find the maximum area. So we're trying to maximize the area of if this is x and this is y, we're trying to maximize the area x times y. And then you have given a constraint. Which is your perimeter. And the constraint is the perimeter is fixed at 48. So the perimeter is x plus y plus x plus y. 2x plus 2y equals 48. I suppose you can write that as, I don't know, x plus y is equal to 24. So in Calc 1, what we needed to do is we needed to use a constraint so that we can rewrite the area as a function of just one variable. And then we would find the max and min and go from there. But we're dealing with a function a with two variables, x and y, right? So instead of doing it the way we would do it in Calc 1, let's go to Calc 3 now, where we're going to consider this as a function of two variables, and then we got a constraint 24. And what I'd like to do is I'd like to try to get a picture of this. And this picture is going to have to be in 3 dimensions. But there's something weird about the other graph, the x plus y is equal to 24. That looks like it's just going to be in 2 dimensions, I think. So, yeah, we want to see where they intersect. Actually, we want to see where they intersect at the largest value. So let's see what we could do with a picture.
Can we write x plus y as a function here?
We generally don't, but we might consider that a little bit later on, x plus y as a function.
So I just write x plus y minus 24.
You could say x plus y minus 24 is equal to some function. But let's not write it as a function yet. So let's start with this graph z is equal to x times y. It looks like a saddle. Well, if we cut it with this rectangle, and the rectangular region is from -2 to 2, -2 to 2, that's your x and y region. If we do it like that, we'll see the max and mins. But that's not our region. What we want to do is we want to see how this would look like with x plus y is equal to 24. So let's also graph x plus y equal to 24. It's out of range. Let's see, zoom out. We're not quite there yet, so what I'm going to do is I'm going to distort it a little bit. Let's go from -32. That might be a little big, but let's see. 32, -32. And let's go from 0 to 32, 48. Maybe 48. Let's go to 100. Let's go to 200. Okay, so if we look at this graph over here, maybe we'll make this blue. So it looks like we're trying to look for a maximum sort of thing. It looks like at some point here, it's going to attain a little maximum, right? And I think more or less that's what we're looking for. We're looking for a place where we might be able to find the maximum. Now, the thing about this graph is that it's kind of hard to visualize. But it looks cool, so let's take a picture of it. Well, do you guys know what we're up to here? I know we're up to no good, but so it looks like by looking at this picture, we can we see the picture? Or possibly be interested in that point. So this is the graph. The yellow is the graph of the area function, and then the plane here is the graph of that. And maybe the height of this thing is going to be the largest value for the area function given this particular constraint. since this is really, this thing makes a lot more sense. This constraint makes a lot more sense as a function of x and y on the plane. Is there any way we can view this graph as something that's on the plane? Do you know what I'm asking? No. Close. Projection. What's a projection called when we want to project it down to the xy plane? Do you remember when you have a graph in 3 dimensions and the projection you're not going to project. We want to make cuts so that it's projected down the xy plane. What? Level curve. Yeah. So if we take a look at the level curve, maybe we might see something that's related to this. So let's take a look at level curves. And let's do this on a different graph. So x plus y equals 24 is one level curve. We're going to focus on this for a minute. Looks like it's far away. Let's zoom out. There we go. So we need some level curves for that other graph. So there's one way to approach that. One way to approach that is we can graph it like z equals x times y. But instead of graphing, this is going to graph a surface. So instead of making sure that it doesn't graph a surface, let's take a look at the contour plots or density plots. So we get this picture over here. And if I click on any of these contours, if you look to the right over here, it gives me my xy point, but it also gives me my value of the height. So like this value of the height is negative 285. And if I look at this, this is negative 190, and this is negative 95. So what I'm concerned about is, it looks like they intersect at some places, and if I draw more curves, it looks like they can intersect at a bunch of places. But there's going to be one special place where they intersect, and I'm going to take a guess at what those might be. So I'm going to make a bunch of level curves that I'm going to create myself. And I'll create that by letting my function x times y, f of x function, equal to some constants. And let's make it all the same color. So then I'm looking at these functions, right? The blue functions now. Actually, they come on both sides, top and the bottom, or first and the third quadrants. Let me add a couple more. Oops, I need to add more. $130? Maybe another one, 140. So what does it look like I'm trying to do?
Find a tangent.
Find the tangent. Yeah, so let me clear some of this stuff out. Let me clear this out for, clear this one out. And let's just focus on these ones that I just made up. I just wasted a whole bunch of them here. I'm more concerned about what's going on here. So it looks like I got 140 and 150, a height of 140 and 150. At some number over here, if I just change this one number, instead of going 140 or 150, 145. Let's zoom in. So now I change the color of this to be the red line. The pink line, I don't know if you can tell, the straight line over here is magenta colored, and this is red. Maybe I should change it to green. It's harder to see. Black. All right, 140 what? 144. Oh, there you go. So it looks like 144 would be a good place to look. Okay, so the idea is to look for where the graphs are tangent to each other. Remember what that's called when two graphs are just like kissing? It's called a kissing graph. Did we talk about that here in this class already? Once. I thought I mentioned it a bunch of times. Maybe just in my head I mentioned it. I forgot to say it out loud. So these graphs are kissing. What else can we say about when the graphs are kissing? What can you say about what they have in common? They're going to be equal at one point, so that's probably the height that we're going to look at is going to be one of our keys, and the height is probably going to be that number that we let it equal to, 144. What else can we say about the graphs themselves when the graphs are kissing? They'll set them equal. That's the answer. Anything else? Shape of the graph. Let's do some calculus on the graph.
Is the slope the same?
Slope, the tangent. Tangent lines are probably going to be the same, right? So the tangent lines are probably going to be the same, or at least parallel. And what's that say? What's perpendicular to a tangent line? What's perpendicular to a level curve? Yeah, but if we have a function in two variables and we have level curves, what's that special vector that's perpendicular to a level curve? The gradient. So it turns out that the gradient's going to be perpendicular to a level curve. So it turns out that the gradients should be the same. The gradients of what? Of the gradient of the original function and the constraint, right? So let's see. I don't know if we can do a picture of this and put it in our notes. Let's zoom out a little bit. So aside from the three-dimensional picture we have, we can kind of focus down on a two-dimensional picture. I think I spent way too much time on this. I don't think so. So what we could do is, instead of looking at the three-dimensional picture, we'll look at the level curves of a of x, y. That's the function that we're trying to maximize. And we also see the curve of the constraint. And then what we're going to say is that it looks like from here, the a of x, it kind of makes sense to have the gradient of this because this is a function of xy. So the gradient of a of xy should be parallel to, not equals, parallel to the gradient of x plus y equals 24. And I'll put quotes here because this kind of doesn't make sense because their gradient is from a function of two variables. But if we consider this a function of two variables, and you can look at 24 or ignore 24, then we can say the gradient of this as a function. So let's call this g of xy. All right, so that's the whole setup of this idea of Lagrange multipliers. Lagrange multipliers assumes that the gradient of your function that you're trying to maximize or minimize is going to be parallel to the gradient of the constraint. Okay? So for Lagrange multipliers, I'm going to go to the next page here. For Lagrange multipliers, we're going to try to maximize or minimize some function given a constraint. And then we're going to describe the constraint as a function that's equal to a constant. And what you're going to do is you're going to assume that the gradient of the function is parallel to the gradient of the constraint. But the way we're going to write this is with an equation. I'm going to leave a space here. And we have two vectors that are parallel if one of them is a scalar multiple of the other. Right? So if we take g, for example, and then we just multiply it by a scalar, then we can say that these two vectors are parallel. And the scalar that they use is a Greek letter called lambda, which is L, stands for Lagrange, and this is your Lagrange multiplier. Okay? So what you're going to end up here is 3 equations and 3 unknowns. If you take a look at the gradient, remember that the gradient is a vector, f sub x and f sub y, times lambda times the gradient g sub x and g sub y. By the way, all these have the variable x and y. So then you have 3 variables that you're looking for. X and y. And then there's also this unknown lambda. So we have 3 variables. We're going to need 3 equations. And that's fx with x and y is equal to lambda times gx with x and y. So that's the first component of your vector. And then you have fy equal to lambda times gy. Well, from this equation over here with the Lagrange multiplier, I only came up with 2 equations. To be able to solve for this, we need 3 equations because we have 3 unknowns. What do you think our third equation is going to be? No? What? No? 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 No. The third equation will be your constraint. It doesn't have a lambda in it, but it still has an x and a y that we're going to need to eventually solve for. Now the concept of Lagrange multipliers is basically this, which makes it simple in theory. But the actual practice of solving for these things is not conventional, or not. You know how we look for a step-by-step process and then we solve for it? Well, the step-by-step process is given here. Now the solving for it may lead to some unconventional ways to try to solve for x, y, and lambda. By the way, there's 3 things to solve for, but it turns out that solving for lambda is not important. What's really important is finding x and y, because that's going to give you your solution, your answer. So, solving for lambda sometimes will make it easier to help find x and y. So if you find lambda, then there's no harm to that. But if you don't find lambda, then that's not a big deal. Okay. All right, so let's go back to our example. Where we have a of x, y equals x times y. And then your constraint is x plus y equals 24. And what we're going to do is we're going to assume that this is g of xy is equal to x plus y. And then we can assume this is f, or we can just keep it as a. Is that okay? Okay. So the gradient of a is equal to the derivative of xy with respect to x is y. The derivative of xy with respect to y, x. And then the gradient of g is equal to 1 and 1. That's going to be easy. So what do we have here? We have your 3 equations would be y is equal to lambda times 1. X is equal to lambda times 1. And then x plus y is equal to 24. Here are your 3 equations. We're solving for x and y.
So we know that both x and y are equal to lambda, so 2 lambda is equal to 24.
So we know that both x and y is equal to lambda, so lambda plus lambda is equal to 24. Lambda is equal to 12. Okay, so that lambda we found, but it's not going to be important for us. But we put it back into x and the y. X is equal to lambda, y is equal to lambda. And so here's your solution. So if we make this a 12 by 12 fence, it has a perimeter of 48, and this will be the maximum volume. The volume, by the way, or area, max area, is equal to A evaluated at 12 comma 12, which is 12 squared. Cubic or square feet if we're dealing with units. Okay? So that turned out to be a really easy example. Any questions? Let's try one that maybe might not be so easy.
So when you find x and y, you just evaluate the function a of x, y at those points?
It depends what they're asking for. If they're asking for the dimensions, then you say it's 12 by 12, so it's x and y. If they're asking for the max area, then you put it back into the equation to get 144. So it depends on what the problem is asking for. And the problem may be asking for different things. All right. Any other questions? So I just checked, and it looks like you only had oh, by the way, where are those graphs? Oh, they're down here? No? There it goes. Oh, so by the way, we guessed 144, right? Yeah, 144. All right. I was opening up one of your homework problems. Homework. So 14.8. Oh, there's only 4 problems. Let's do one of them. Let's do number 2. So here they're looking for a maximum and minimum value. So they must be looking for a number here. Let's see. I guess they're looking for maximum and minimum value for all of them. So if you can imagine what this might look like, this is a saddle, and it's called a hyperbolic paraboloid, and it turns out that the level curves are hyperbolas. And then this here is an ellipse, right? It's got x squared and y squared, and then it's 1/4, so it changes the radius for the x or y direction. And so we have, we would have those, if we take a look at the level curves, we'd have hyperbolas and ellipses, and we can imagine how that might look like with the common gradient. The kissing, you can imagine where those graphs might kiss. We'll get a picture of this later after we work it out, but let's try to work it out first. So we will assume that our constraint is going to be our g function, and our f function is going to be our f function. So fx, well, I'm going to call it the gradient, and just write a vector out of this. It's going to be negative 2x comma 2y, and then your g is going to be
Wait, wouldn't it be the other way around?
I don't know.
Okay, it's holding. No, that's fine. Fine.
Because
I think
is that okay?
That's right.
All right. So now this one with an x, it'll be 1/2 x, comma 2y. Right? And then we're ready to build our equations. You know, the gradient of f equals lambda, gradient of g should be in your head. If you want to write it down, go ahead and write it down. But I'm just going to go ahead and write my equation. So that would be the x component is equal to lambda times 1/2 x. Is that right? And then 2y is equal to lambda times 2y. And then it looks like lambda is going to equal to 1. Is that what you guys are saying? Oh, there, I have my third equation. Let's see. Let's start solving for this. If we divide, assuming, we have to assume that x doesn't equal to 0 here. Assuming that x does not equal to 0. We don't know that. We'll make an exception and then maybe come back and revisit the idea that x, what if x was equal to 0? Then we'll include that as a possibility. So assuming x doesn't equal to 0 because you're going to divide by x, lambda is going to equal to what? 4? Negative 4? Or y is equal to 0. So over here also, assuming that y does not equal to 0, then lambda will equal to 1. So these two are in contradiction already. So we can't assume that both x and y are equal to 0, otherwise that's not going to work. So now here, let's take it a step further. Now let's assume that x is equal to 0. If x equal to 0, then this is nothing. 0 equals 0. We'll use a second equation. That doesn't say anything either. Let's use the third equation. If x equals 0, then 1/4 times 0 squared is equal to y squared. Oops, plus y squared is equal. So y is equal to plus or minus 7. So we have possible values for x and y by letting one of them equal to 0. And so the other choice is that what if y was equal to 0? Again, the first equation doesn't have any y's in it, so it's not going to matter. So we got 1/4 x squared plus y squared equals 49. So 49 times 4, I don't know what that is. But x will equal to plus and minus, I'll go 14. Is that right? So it looks like we have 4 possible points. We have 0, 7, 0, negative 7, 14, 0, negative 14, 0. All right. So what we're interested in, remember, is to maximize and minimize the function. So if I take these numbers and put it into my f function over here, 0 in for x and 7 in for y will give me 49 plus 0. And then if I put negative 7 in for y, it's also going to be 49. And now we're going to try putting 14 in, 0 in for y, and 14 in for x. Negative. And then if we put a negative 14 in for x and 0 in for y, we're also going to get negative. I guess 196 is our minimum and 49 is our maximum. Okay? If you cared about the specific points, they're right here, but the program itself is just caring about the value, so that's all we're going to care about also. So let's put in the value 49 and 196. Let's see what the computer says. Maximum is 49, the minimum is 196. All right? So let's take a look at this from a graphical perspective, and by looking at the level curves. Well, if you can't, because lambda is negative 4. If you plug that into here, then you're not going to get a value for anything.
Well, if you have 1, right? You just get like negative.
What really matters, like x and y aren't
Yeah. So also notice that we didn't solve for lambda once we've gotten into this other realm of saying, oh, what if we'll try x is equal to 0? We didn't bother solving for lambda anymore. Well, we had them, but they didn't give us anything. Yeah, so let's see the picture. We have the constraint is what was the constraint again? It's 1/4 x squared plus y squared equals 49. And then let's start by drawing the graph, just the general contour plots for this graph. What is it, y squared minus x squared? And I have to say that I want contours. All right, I'm supposed to get paraboloids going the other direction as well. And you can see that this paraboloid over here, hyperbola, this hyperbola over here, if I move that over to this graph, it looks like it might be kissing at that point. And that's at the point x is equal to negative 14, right, which is one of the values that we had. So I'm going to go ahead and hide this now and put in specific values that we found. What were some of the heights that we found? 49? And negative 196. So this graph, y squared plus x squared is equal to 49 is a hyperbola that's going to be kissing at that point 0, 7. Right? At 0, 7, that's one of the important points that we found. And then if we find the other graph, what is it? Negative 196. And here's your other hyperbola that's kissing on this side. Okay? So if you compare that with the rest of the hyperbolas that are involved, Should have more. Let's see if we can do a density plot. You can see kind of shadows on the other side. I don't know. Maybe that's a little too much. All right. You want to put it in 3D? Oh, you mean the density? Oh, not the contour plot, but in 3 dimensions. I don't know if it's good old. So this is your saddle. So this is going to be an ellipse, but there's no z in it, so it's going to be dragged up and down. So it's an elliptical cylinder. We need to zoom out sufficiently enough. We need to sufficiently zoom out, and we need to. You kind of need to include up to negative 196 in here. Let's go 200. Negative 200 to, this only needs to go up to 49, but let's go up to 100. So if you look at the different parts of this, let's make this one lighter. You can kind of see those parabola highs and lows, right, of where they would intersect. Let's see if we can make this clear, transparent. You see the same thing. It's those highs and lows of the parabola will be the places where they would intersect. So, is that a good visual? So let's stop it here and take a couple of pictures and put it in our notes. So from a two-dimensional perspective, this is what we're seeing. We have the graph 1/4 x squared plus y squared is equal to 49. And then we have two level curves over here. The first level curve would be y squared minus x squared is equal to, this is the 49 one. And then the other one, yeah, y squared minus x squared is equal to negative 196. And so those are the places where the graphs would have the same or would have parallel gradients. Now let's take a look at the other picture. Well, I have to say that the problems that we were doing are pretty easy, and there are going to be some times where solving for the 3 equations and 3 unknowns would be, you need some certain tricks that you may have not even thought of. So, integrals. Did you say integrals? So this is x, y. Are these? Is this in there? So this is your x-axis. This is your y-axis. So this must be x is equal to 7. No, is that right? 7. 0, 7, 14. 14 is the x, right? 14, 0. And then the y value is 196 negative. And then this up here would be your point. X is equal to 0, y is equal to 7, and then z is equal to 49. Okay? All right. So what's cool about Lagrange multipliers is that it easily extends to, this is an example of function of 2 variables, but it can easily extend to a function of 3 variables. So you have one of those. I'm kind of hesitant to do this as one of your homework problems, but let's make it easy and just do a homework problem. Uh-oh.
It's going to be different numbers. So we really
So this is probably, I think this might be one of those cases where you might be asked to find to do some weird manipulation in solving for the x, y, and z. So let's, maybe not. Let's take a look at this. Your function is f is equal to 10x plus 10y plus 5z, and then your constraint is 5x squared plus 5y squared plus 5z squared is equal to 45. So this is happening now in 3 dimensions, and our function is really living in the 4th dimension because it's a function of 3 variables. But it's going to be the same deal. You're going to have 4 equations now and 4 unknowns. The unknowns are x, y, z, and lambda, because there's 3 variables in lambda. Yeah? Yeah, so we could graph a 3-dimensional contour graph, and this is where we'll see the kissing happen. Because there'll be kissing surfaces now, not just curves. There'll be tangent surfaces. So we'll graph this in a few minutes after we solve for this. Yeah, we have time. So we find our gradient with respect to f, or gradient of f. So that's 10, comma 10, comma 5. So having constants is a nice start. And then the gradient for g is 10x, 10y, oops, yeah, 10z. So we're going to set them equal to each other to get our equations. You get 10 is equal to lambda times 10x. 10 is equal to lambda times 10y. 5 is equal to lambda times 10z. These are 3 equations, but we have 4 unknowns, x, y, z, and lambda. So our 4th equation, 5x squared plus 5y squared plus 5z squared is the constraint. All right, so immediately as you're trying to solve for this, we can see lambda is equal to 1 over x. Lambda is equal to 1 over y. Lambda is equal to 1 over 2z. I want to put this into the 4th equation to help me solve for this, and it doesn't look like it'll work out nicely that way. What should I do to try to solve for this? This is where you rack your brain and hurt yourself. Why don't you solve for x, y, and z instead, right? And then, because there's an x, y, z in the other equation. Maybe we should have done that in the first place. X is equal to 1 over lambda. Y is equal to 1 over lambda. Z is equal to 1 over 2 lambda. So let's put that into the 4th equation. Now we have x, y, and z. So it looks like we're on our way to solve for lambda. 5 times 1 over lambda squared plus 5 times 1 over lambda squared plus 5 over 1 over 2 lambda squared is equal to 45. I suppose we could have just knocked off the 5 and called it 9, right? So there's 3 of these. No, there's 2 of these. 2 over lambda squared plus 1 over 4 lambda squared equals 9. We have to combine common denominators, so I need to multiply this by 4 over 4. So that's 8 plus 1 over 4 lambda squared. So that's 9, right? So the 9s would cancel, and there's still a 4 over here. What? What did we do? We multiply the 4 to one side, and then we still cancel the 9 and 9. Is equal to 4. So lambda squared is equal to 1/4. So lambda is equal to plus and minus 1/2. All right, 1/2. We'll say lambda is equal to positive 1/2, and then we'll get some positive values. I don't think it'll make a difference. You get x is equal to 2, y is equal to 2, z is equal to 1. I suppose we can include lambda here too. So this is one set of solutions. Let's assume that it's negative. You get x is equal to -2, y is equal to -2, z is equal to -2. Here's another set of solutions. But it turns out that I guess when you put it into the original function, x, y, and z are all going to be squared, so it'll turn out to be positive anyways. So let's, is it? No, it's not. It's right here. Sorry. Not all positive. So f of x, y, z, this is the function that you have in the first place, is equal to 10x plus 10y plus 5z. -1? -1, right? Yeah. Okay. All right, so this is our function. So let's put the first set of numbers in. F of 2, 2, and 1. So that's 10, 20, 45. Is that right? Looks like this is just going to be negative. Did I add that right? 10 times 2 is 20, 10 times 2 is 20, 5 times 1 is 5, 45, yeah. So it looks like it's 45 and -45. Let's check. And then let's take a look at the graphs. So that looks right. So let's take a look at the graphs of the original function. And for this one, we have to look at the level curves already, level surfaces already. Let's graph the constraint first. We got a 5x squared plus 5y squared plus 5z squared. I guess we should have said it just is equal to 9. So it's a sphere. We should have known that, right? And then now let's take a look at a couple of planes. We got 10x plus 10y plus 5z equals to, what were some of the values that we had? 45? So we got one of them. Clearly it's tangent. I don't know if it's clearly, but it's tangent. And then we'll throw the other one up there with a negative 45, and that is also tangent. Okay? So the values themselves are these values over here. We can't see up or down in fourth dimension because the 45, that value 45, actually lives in the fourth dimension as either time or temperature or whatever it is that we're trying to describe. So we can't visualize that as being higher or lower. All we could do is trust that this number over here is 45 is bigger than this number, negative 45, and that's how you find your max and mins. Okay? So we got a dose of Lagrange multipliers here. Your quiz tomorrow will not cover Lagrange multipliers. Your quiz tomorrow will be on finding critical points and finding using the second derivative test, which somebody might put up on the board so you don't have to memorize it. Just the statement of the second derivative test, you know. Yeah, it's just, yeah. So maybe we'll have somebody put it up on the board before the test starts. Okay? Or what? Double integrals?
I've done 3 already.